Hello students, so in this lecture we shall be discussing about the factors that affect the creep properties. So we'll start with stress dependence of creep. Now what happens is at low stress the stress exponent if is equal to 1, consider that low stress where the stress exponent is equal to 1, so it leads to NH or cobalt creep. At higher stresses, on the other hand, where the exponent is, for example, it's 4.2, in that case, the creep is controlled by dislocation climb. At least the creep is controlled by dislocation climb. Secondly, the diffusional mechanisms are common in ceramic polycrystals, are related to two factors: diffusional mechanisms, which are common in ceramic polycrystals, related to, there are two factors which are related to these diffusional mechanisms. The first one is, let's call it as A. The first one is, in many ceramics, the inherent resistance to dislocation light is maintained even at high temperature. So, in many ceramics, the inherent resistance to dislocation light, I'm writing it as DG, dislocation light is maintained even at high temperature. It's maintained even at high temperatures, so that the mechanisms involving dislocation light is suppressed. So that the mechanism involving creep through dissolution light is suppressed. And the second factor is, the ceramic polycrystals typically have very small grain size. Ceramic polycrystals typically have a small grain size. So the differential mechanisms are enhanced. So the diffusional mechanisms are enhanced. So diffusional mechanisms are enhanced. So this was all about the stress dependence. Another dependence.
बाबा सबसे अच्छा और कम झिकझिक में पर्सनल लोन कहाँ मिलेगा?
Move on to the temperature dependence. Now, temperature dependence is firstly it is characterized by activation energy, which is equivalent to that of diffusion. Secondly, the coupled diffusion in ionic ceramics to maintain charge neutrality, it leads to ambipolar diffusion. Coupled diffusion in ionic crystals to maintain charge neutrality. That means if there is a diffusion taking place of the cation, there has to be a corresponding parallel diffusion of the anion, so that the charge neutrality is maintained. This leads to something called an ambipolar diffusion. And that is parallel transport through lattice and grain boundaries. That is parallel transport through lattice and through grain boundaries. The third point about temperature dependence is the creep rate is controlled by species which move slower on its faster path. Creep rate is controlled by species which moves slower on its faster path, which moves slower on its fastest path. The fourth point is the creep in ionic ceramics can be influenced greatly by ambivalent impurities, at least in the temperature range where the diffusion is extrinsically controlled. So the creep in ionic ceramics can be influenced by valent impurities, impurities having some sort of valency involved, at least in the temperature range where diffusion is extrinsically controlled, at least in the temperature range where diffusion is extrinsically controlled. The fifth point is the creep rate in oxide ceramics can be influenced by oxygen partial pressure. Creep rate in oxide ceramics can be controlled by oxygen partial pressure. Now, this dependence arises mainly because creep is diffusionally controlled and the slower diffusion oxygen species move through the lattice. So,
अब आप एक्सेल का काम आसानी से अपने फोन से कर सकते हैं.
so the reason of dependence upon the oxygen partial pressure is mainly because of the fact that the creep is diffusionally controlled and the slower diffusing oxygen species and the slower diffusion oxygen species move through the lattice by a neutral interstitial mechanism. By something called neutral interstitial mechanism. So what we actually get is the dependence of a creep rate on the square root of the oxygen partial pressure. Is in terms of and it is understood in terms of the number of oxygen interstitial available for diffusion. Is understood in terms of number of oxygen interstitials available for diffusion. The next dependence of creep is on grain size dependence. Now, there is a parameter which is we define the parameter of the dependence upon grain size. That means if we assign a parameter m, so when m is 2, it means that we are having an NH creep, and it is basically the fact that it is d to the power minus m dependence. So when m is equal to 2, it means we are having an NH creep. And when m is equal to 3, then it's a global creep. This is the grain size. So whether it will be the relative rates of grain boundary and lattice diffusion, they are distinguished by the difference in grain size dependence. This we have previously explained. So this parameter is important, d to the power minus m. If m is equal to 2, it's an NH creep. If m is equal to 3, it's a global creep. Now if we plot the steady state creep rate with respect to O2 partial pressure in the previous case, then we get a plot like this, a linear plot. Whereas if we plot the steady state creep rate with respect to a grain size, for example NH, then we get for this is of course for m is equal to 2. Next is the effect of porosity.
अब आप एक्सेल का काम आसानी
Effect of porosity on the creep. So the increase in porosity That means the volume fraction of porosity. If we increase the porosity, the rate of the creep is supposed to increase. So what happens here is that the porosity, if it increases, then it also increases the load bearing cross sectional area. Of the specimen, and which decreases, and the load bearing cross section area is found to decrease with increase in porosity, and so it leads to a higher creep rate. So the material creeps rapidly. And now these porosity effects are expected to be greater in materials for which the creep rate is more stress sensitive, that is higher stress exponent. So porosity effects are expected to be greater in materials for which the creep rate is more stress sensitive, for which the creep rate is more stress sensitive. That is a higher stress exponent. Now, apart from that, other factors which affect creep are soft intergranular phases, now intergranular phases softens or melts at high temperature, characterized as IG phases. So IG phases, they softens or melts at high temperature, and which causes a substantial reduction in strength and creep resistance may result. So it results in a substantial reduction in strength, and hence creep resistance may result. Substantial reduction in strength and creep resistance. Strain is produced primarily by rigid sliding of the solid grains. Strain is produced primarily by the rigid sliding of the solid grains. Which is made possible by shearing in the soft intergranular faces, which is made possible by shearing in the soft intergranular face. Now,
बाबा सबसे अच्छा और कम झिकझिक में पर्सनल लोन कहाँ मिलेगा?
बेटा तुम्हारा
the rate at which deformation proceeds is determined primarily by the mechanism which accommodate the sliding at these grained interfaces. So the rate at which deformation proceeds is determined primarily by the mechanism which accommodate the sliding of those grain interfaces. Which are jammed together or pulled apart as a result of sliding, which are jammed together or pulled apart as a result of the sliding. So if we draw a diagram of the different grains, we are considering grains to be hexagonal, although they are not, just to make things more clear. So the intergranular phases are, say, found here. These are the intergranular phases. So when we are applying a stress, say, tau in this direction and tau in this direction, so there is diffusion taking place. So there is also liquid flow. There is diffusion, and there is cavitation, and these intergranular phases, they move, they slide. Some atoms move to the intergranular phases, and this is how the thing works. So basically, another point is the diffusion of the solid reticular phases is Koval creep. Diffusion of solid through the intergranular phases, it gives rise to Koval creep. Percolation of flow of the intergranular phases which occurs when the intergranular phases is so soft that it behaves like a liquid, which occurs when the IG phases are IG phases are so soft that it behaves like a liquid. The nucleation and growth of the cavities at these places where trichinoid phases are stressed in tension, and this is a primary mechanism of creep failure. So, nucleation and growth of cavities, that is called cavitation, at these places where the IG phases are stressed in tension, is the primary mechanism of creep failure. This is the primary mechanism of creep failure.